Okay. First off, I think I emailed, oh, somebody must be sick today. I think I emailed everyone on what, Friday after I graded the quizzes. They were surprisingly good. Not that I didn't expect you to do well, but usually that content is, 2/3 of the class kind of gets it. The rest of them were dragging a little bit on it, but the class as a whole did pretty well. But the more important thing was everybody did it. I don't remember the last time that happened. Like technically everyone was in attendance of a class at the time of the class. It was like sign of the apocalypse, I think. So, but yeah, I do apologize for having to cancel in person. We're trying to work out with the doctors to get all of her appointments early on at like 8 a.m. on Thursdays. So this coming Thursday, the first part of class, we're going to be doing a thing with 3D printing. So our Makerspace guy is going to be here because we're going to create a competition in the classroom. And then we'll pick up from there like around 30 minutes in. That just gives me a little more wiggle room. I think I told you guys before, my wife's really sick. So she has stage 4 bladder cancer. So I kind of want to be at all the doctor's appointments, but that doesn't mean you should be impacted. So we're trying to work out the schedule with the doctor. So bear with me a little bit. And then we'll be able to hopefully not have like last minute cancellations and stuff. Okay, so having said that, I do commend you on the quizzes because they were good. I want to say maybe the low grade was like an 80 or something like that, and that was just multiple like little math problems or used the wrong pattern. Actually, probably used the wrong pattern because like little math mistakes, I probably gave you a 9 out of 10 for that question. So good work there. All right, so let's see where we left off. I need to compress a couple things. Plus, I'm guessing we're probably looking forward to actually getting into programming stuff pretty quick, right? All right, so talked about it. All of this. I want to skip that crap. We've talked about high level, low level, machine level code, right? We looked at Hello World and Linux, compiled versus interpreted. Looked at a compiler converts from a high level language to a low level language. Okay, probably didn't so much talk about this yet, loosely typed versus strongly typed. And I'll probably try to show this by actually an example today, because I do want to dive into the coding stuff some today. All right, so again, we're looking at programming languages from a bunch of different angles. And all these tend to be truths of a language. And I advertise that computer programming is the skill set. The actual language doesn't matter. So with that in mind, being able to take a programming language that's sitting in front of you and saying, okay, well, let me just get an idea of what kind of language am I dealing with here. That's going to give you a lot of information about how you can wield that language to solve problems. All right, so if you know it's an interpreted language, you can pretty quickly guess that it's a loosely typed language. Those tend to go hand in hand. You could also pretty quickly say that, well, if it's interpreted and it's loosely typed, it's probably a lower performance language. They're not probably making video games out of it. Good example for that be like Python. So the Python programming language is an interpreted language, super popular language, right? It's an interpreted language. It's a loosely typed language. It is a, what else have we talked about with, it's a high level, interpreted, loosely typed language. That gives us this information that Python is relatively slow compared to other programming languages like C, which is high level, compiled, and strongly typed. It's going to be much more common to see like a video game made out of C instead of Python. Having said that, our computers today are really, really, really fast. So for 99% of the applications you might write, you're not going to notice the difference between an application written in Python versus an application written in C. They're going to both feel instantaneous. All right. In fact, a lot of our artificial intelligence, machine learning software libraries are done in Python. And they are heavy computation things that really push the computer a lot, yet they're using an interpreted language to do it. All right, so loosely typed, and I actually kind of remember we did talk about this, didn't we? I think I probably talked about like Tupperware containers, labeling it for your taxes versus your shoes. So loosely typed means that you don't have to label a bucket for what you're going to put into it before you put something into it. So you're allowed to put a number into a variable and then 10 minutes later put a string into a variable. Loosely typed languages allow you to do that. I would say that will rarely ever make sense. So realistically, a loosely typed language is more going to be something dealing with syntax. When you create a bucket to remember something, remember, way human beings solve problems, we do memory, asking questions, repetition. 100% of programming languages have facilities for those three things. So when we're using a programming language to create a named chunk of memory to hold something, chances are we already have a pretty good idea of the kind of value we want to put in there, right? We want to put in, like if we have a variable called my age, we're probably going to be putting a number in there. All right. If we have a variable called my name, we're probably going to be putting a string in there. All right. You probably wouldn't have a variable named my age and put a 15 in there and then 5 minutes later put the string Mike, because it's allowed in a loosely typed language. But now all of a sudden the name of your variable and what's in it no longer correlate. That makes some sense? All right. So this is really more of a capability of the language than something that I'd encourage you. I would call it poor programming practice to create a variable with the intent of holding one kind of value and then switch it to a different kind of value just because you can. Your names of your variables should strongly influence what your guess would be is inside of that variable. But in loosely typed languages, when you do define that bucket for holding information, you don't have to let the computer know what kind of value is going to be in there. You're relying on the computer being able to figure it out the very first time it goes to look at that variable. It looks in there and says, you have a number in here. We're going to treat this guy for mathy type stuff. Whereas a strongly typed language requires you to define, here's my variable called my age. It's built for holding integers. I have to specify that in the syntax, the code that I'm writing. I have to tell the language that. All right. All right. So we were looking at some history of language stuff, right? I think I actually have it written higher up. Oh, maybe not. We've seen this at some point, right? We were working through this. Forget about the stuff over here. That's so this isn't the slide I was working with, but this is fine. So we talked about one of our early base programming languages called C. And that's actually the language we're going to be using in here. We're going to be using C and C++. C++ just has object-oriented extensions to C, and we'll talk about those. But if we just assume that our base programming language for all modern programming languages, the C programming language, and then all of those languages today kind of took a lot of influence from C. In some cases, 99% of their influence came from C. The syntax is the same. So C is something called a procedural language. So just like we've been looking at these different, through these different lenses, there's three different kinds of programming languages. There's procedural, there's object-oriented, and there's this kind called functional, which we're going to kind of ignore in here. You're actually going to look at a functional language when you take the 470 language theory class. We use a functional language in there called Scheme. But the difference between a procedural language and an object-oriented language, we actually just create a slide for this guy. I'm sure we'll bump into it soon. All right, so we want to remember that the job of a programming language is to allow the human being to tell the computer what to do. At the end of the day, that's what the programming language is doing. It's giving us a way to boss this guy around. Okay. So the best way to describe procedural versus object-oriented languages, and really all of our modern languages are object-oriented. Procedural languages are where we started. That isn't to say, like, for instance, we're going to be, let's say we're using C++ in here. We're going to be using an object-oriented language, but we're going to be writing a lot of programs in a procedural manner early on. We aren't going to take advantage of the object aspect of that until certainly after midterms. So what does this ultimately mean? Again, programming languages are there so that human beings can tell a computer what to do. So what we expect them to do is have facilities that allow us to solve problems the way we're already used to solving problems, and then use this tool, the programming language, to tell the computer what to do. So you go back into, let's call it the 50s, the 60s, the 70s, the very, early days of computer programming, really the early days of consumer computer programming was probably the late 60s, early 70s, something like that. So when you go back to an early language like C, which has been around since the, late 60s, probably earlier, but let's just go with that for this example. The problems we were solving with that language, the things we were telling our computers to do, were very simplistic compared to the things we're telling our computers to do today. Part of that is because our computers today are a lot faster than the computers were back then. So the computers today are much more capable than the computers were back then. And that kind of drives a couple of other things that we're going to talk about here. We talked about memory some last time, right? The cost of memory, expensive, blah, 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 all that stuff. I feel like I've gotten, let me actually check something here real quick. I feel like at some point, this is us, right? All right, so what I'm going to do is I'm just going to steal this slide. We're going to close this one. I kind of recall the other day that iCloud went down or something, so I had to create a copy of it. So rather than lose it, I just kept trucking. I just saved it as a copy, as a just in case. All right, so the problems we were using, the problems we were solving with our computers were much simpler problems, probably more than just printing out hello world. But something we would consider to be let's just use video games as the example. Something we would consider to be a fairly complex video game today wouldn't even have been something that would have been even close to considered in the 60s, 70s, 80s, 90s, early 2000s, so on and so forth. We just have so much more computational power today. Our speed and power is increasing at a slower pace today than it was for those first bunch of years. So late 90s into probably 2012, something like that, 2014. During this time, it seemed like every 5 minutes, something faster, better, yada, yada, yada was coming out. So the things that we could do last year, we can now do so much better this year. What we've seen since then is our computers aren't necessarily getting that much faster outside of graphics cards. What we're really seeing now is our computers, our processors have more cores, right? Instead of having one super fast core that's operating at 3.5 gigahertz or something, we have 4 of those cores operating at that speed, with a lot of them have, kind of automatic transmission built into it, where they'll slow down to preserve battery life when you don't need the extra horsepower, and they'll speed up when you're really pushing it because they assume you're plugged into a wall, that kind of stuff. So our more modern performance increases tend to be that our computers can do more than one thing at once. And we'll talk more about that when we get to it. I don't want to throw too many random things, but I'm kind of creating a foundation that we're going to build this stuff on top of. But that's really the kicker. If you go back to a super fast processor from 2000, let's say 2000, you may have had processors that had speeds that were, well, let's go with like 2006. 2006, you probably had processors who had speeds that were competitive with the speeds we see on processors today. You can't just look at the gigahertz rating of a processor and say, and think of that as like miles per hour for a car. There's more to it than that, because there's also the underlying architecture. We've looked at like i386 assembly architecture for Linux, for instance. We looked at that Hello World program. So different architectures have underlying performances associated with them. Really, when we talk about a gigahertz rating for a processor, the speed of the processor, we're really talking about how many instructions per second it can process. But one instruction may be more or less powerful depending on what the underlying architecture is for the computer. So you can't just say that a 3 gigahertz processor is flat out faster than a 2.5 gigahertz processor. You probably could say a 3 gigahertz processor is faster than a 2 gigahertz processor, but it's somewhere in there. There's a, you can't just look at the maximum speed type thing. But what we have had more recently that we've gotten borderline out of control with is we've gotten this idea of multiple cores, right? You buy a computer today, it's at least a quad core, right? Then you have 6 cores, 8 cores, 16 cores, yada yada yada. I think this computer is an 8-core i9, and i9s have hyper-threading, or they have a new name for it now. So that's actually 16 logical cores in this. So technically I can do 16 things at once on this computer, or my processor is able to have 16 separate instructions occur at the identical time period as each other, as separate computation lanes. So now, are more cores better than less cores? Is 8 cores better than 4 cores? Again, human logic would say, well, more is always better, right? Well, it depends what you're doing with it. Kind of goes back to the old joke of how many people does it take to change a light bulb? Does it matter if you have 50 people standing in line to change one light bulb? You're only going to use one of those cores, right? So a core, you can think of it as like a person, a work unit. Some problems are very evenly divisible, or are very divisible into chunks. For instance, let's say that we were, this joke will make more sense once we get to the winter. But let's say we have a big snowfall on campus, we're going to volunteer as a class to go and shovel the snow. And let's say we have one person who can shovel snow at speed 10. Let's just say that's the fastest snow shoveling speed. All right. But let's say we have this entire class here and we can all shovel snow at speed 6. Who's going to be able to shovel the entire campus quicker? That one person who's super fast at shoveling snow, or all of us working together, each taking a different portion of campus and shovel? That kind of job benefits from being labor being divided. So that's where multiple cores really come in. Same thing with, I'm sure none of you have ever done this, but downloading some video off the internet that's in a format that you need to convert to another format to make sure it plays on your Apple TV or something like that, right? If you've ever noticed, not that again any of you have ever done this, but maybe academically it was a open source documentary on the Bible or something, something that was not necessarily an illegal video, but let's say it was a 2-hour movie and you were having to convert it from MKV to MP4 or something like that, some other format. And I like to do this example with like, let's say this computer versus like a MacBook Air. So MacBook Air, super nice machines, very lightweight. I would say when I'm sitting in front of my MacBook Air, it feels every bit as fast as this computer for normal tasks. If I'm doing email or web browsing or, whatever, it's peppy, it feels good, feels fast. why spend this money on this extra fast computer if they always feel the same? Where you'll actually notice it is in problems like that, kind of like our snow shoveling example. If I go to convert that movie on this computer, it would probably take something like 2 minutes. If I convert that same movie on that MacBook Air, it would probably take something like 25 minutes. Because the MacBook Air, even though the current processors are a quad core, the cores are are lower performance and all this other stuff, they just can't work as fast and they have less workers working on it, is what it comes down to. And converting video is similar to snow shoveling, where you can break the problem down into one processor is going to work on the first minute, another processor is going to work on the next minute, and so on and so forth. So you can have it working on parts of that video conversion all at the same time. So maybe the people who get the most benefit out of these multiple cores are like graphic designers, animation people, maybe something you've seen if you just kind of look at what's happened in like entertainment over the last, let's call it, decade. Whether it's in video games or whether it's in movies and stuff, animated movies are getting more and more realistic. You notice that? Almost to it's a problem. Like, I'm not a fan of the current Teenage Mutant Ninja Turtles series. It's almost fake realistic, but still cartoony. There's something wrong with it. Yeah, there's something wrong with it. I want my old Ninja Turtles. Yeah, so in fact, my last laptop, I'm a big Ninja Turtle fan. I had Ninja Turtles on here. I have to put them back on, but yeah, that's a whole nother story. Don't be surprised if there's an extra credit question on an exam about name the 4 Ninja Turtles, color bandanas, what weapons they have. Just saying, it could benefit you if you had that knowledge. Like 3/4 of the final exam was Ninja Turtle related. So anyways, more recently, our computers, we just keep adding more cores to it. And for those of you who kind of follow computer hardware stuff, every year you'll hear things like, oh, this is 12 nanometer technology, or this is 8 nanometer technology. What does that mean? What is that when they, because we put all these fancy techie terms in front of stuff that's supposed to be awesome, but it doesn't mean anything. It's kind of like the shampoo commercials that say it's, made with real, I don't know, violet oil or something. Like, well, is that supposed to be good? I don't know if that's supposed to be good, but it's made with the real stuff. What is nanometer? What's the difference between a 10 nanometer processor and a 6 nanometer processor? Anybody know? We had somebody in here with 256 gigs of RAM. They should know. They're just stockpiling stuff. Anybody know what the deal is? Go ahead. Is it the size of the CPU itself? Or is it? Well, I'm going to say no, but there could be some aspect to it that does drive that. Go ahead. Sort of, kind of. So when you deal, we have our processors today. We have machines that do what they're called printed circuit boards. All right. So I never seen it. Apple tends to be the advertiser for this stuff. When they announce their new processors, they say the first processor to have 9 billion transistors, yada, yada, yada. Like, okay, transistors effectively a light switch, an on or off switch. Well, is 9 billion of those better than 8 billion? Are you going to use all those switches? I don't know, but more is better. That's how humans work, right? Or at the very least, we like to give, let's give us more power and then let the people figure out how to use it. That tends to be how innovation works. That's how the app stores worked, right? I'd say actually many of you were pretty young when the app stores first went live on smartphones, but the early day of the app stores, you had all these apps from Apple or Android. But since then, it's really been the public that's innovated and come out with these, neat apps that, maybe the core companies, Apple, Google, whatever, didn't really think about, that just required a whole bunch of humans working on similar problems and coming up with cool software that solves problems that Apple didn't know you wanted to solve, that kind of thing. Well, anyways, we have these printed circuit boards. And when we talk about that nanometer technology, it really comes down to how good are our computerized or robotic instruments for printing those circuit boards, how close can we get the little tiny copper wires to each other, or even gold wires to each other before they start creating interference? You know, at what level of microscopic printing can we get to without causing interference? And we keep getting better and better and better and getting them closer and closer and closer. Right now, I think this year is 4 nanometer technology. You get pretty close to kind of the end, right? You know, we've been talking about that for a while in the computer architecture world. Is at some point we're going to need new material. You know, silicon and our manufacturing processes are only going to be able to squeeze so much more stuff into the same footprint. So then we get back to, you know, processor size. So when you open up your computer, you know, it's a little square thing. I don't know, it's like 1.5 inches by 1.5 inches or something. I mean, they could just say, well, let's just make it, you know, 6 inches by 6 inches, and we'll just, now we can fit more crap on there. Great. Okay, well, more crap equals more heat, and now you got to have this giant, you know, fan on it with liquid cooling and all this stuff. And so all this is happening at the same time as we're trying to get our devices to be smaller and smaller and smaller. So, yeah. Well, now it's reversed though, right? So for a long time, phones kept getting smaller. Well, let's just go with smartphones. They kept getting smaller and smaller with still good battery life. And then all of a sudden, you know, because they had to be thin, you know, they would talk about how thin this phone is, because the early smartphones were pretty bulky, bricky type things. Well, now that our batteries have gotten a lot better and the processor technology has gotten better, we've now been able to go back and say, okay, well, now let's start making giant screens again, because we have better batteries that can make the phone still last a full day. You know, whatever that means for the different use cases. You know, so we've been playing this game for a long time, and you know, in different verticals, with the ultimate thing being humans are greedy and we always want more. That's okay. That's, you know, we'll just, you know thyself is the thing. So anyways, our computers today are far, 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 far more powerful than they were 10 years ago, 20 years ago, 30 years ago. And it was, you know, we go back from 30 years ago, it's thousands and thousands of times of exponential growth. Okay. The computers back then were jokes. This is back when a language like C, which was a procedural language, first came into being. The problems that we even imagined using computers to solve were nowhere near as complex as the problems we're solving with computers today. All right. So in those early days, everything was text-based. We didn't have graphics and stuff. There was just a lot of, you know, mathy computation stuff. You know, maybe it was in the very early days, maybe it was like NASA calculating, you know, landing trajectories and things like that, which was just a whole bunch of math really fast. Didn't have to look pretty or anything, just, you know, bunch of computation and here's your answer. Well, now, as we got, as our computers kept getting more and more advanced, and then we, you know, introduced the mouse and, you know, full color displays, and all of a sudden now we have graphical user interface operating systems. Can you imagine a computer before there was graphical user interface operating systems? What if your entire computer, you turned on your computer and all you saw was this? Terminal. That was the entirety of your computer experience. Go ahead.
I went to recently a vintage computer festival this weekend.
Yeah.
And when they didn't have, when they needed to see what was on it, it would type it in real time. So like a big typewriter.
Yep.
20 minutes.
Yep. Was that a printer?
No, it was like acting as the terminal.
Oh, okay. Oh, okay. Got it. Oh, okay. Yeah, on a dot matrix printer. Yeah, I had the little holes on the side of the paper, and you had to look at what the. Yeah. But yeah, this is what computers used to look like. You didn't have a mouse to drag stuff around. You had just the keyboard and you typed. You know, that's what you did. You put in a command and it did something. If you wanted to open up a text editor, I think you saw me do this the other day. You know, I'm in Microsoft Word right now. You know, just a normal text editor. I can do whatever I want. This one's called the VI. But that's how you used your computer. That's how everybody used their computer back then. That was just normal. Today, you can't even imagine, right? Like, why would anybody do that? Yeah. But the reality is that the farther you get into your computer science education, and the more you start using this stuff, you'll actually start recognizing that in many ways, command line stuff like this is still faster. So getting a experience with command line interfaces is a powerful thing. Not that you're ever going to start launching your web browser from the command line. You know, there's plenty of use cases where, hey, using our modern operating systems with the double click stuff, that just makes sense. But there's a lot of things you can do for the command line that just don't make sense graphically. Sometimes when you make something more convenient, you take away some of your power from it. So in any case, that's what our computers looked like back then. So you can imagine that the complexity of the programs was not as high. Today, computers look a lot different. Graphic cards are every 5 minutes getting more and more powerful. So our video games and stuff have a lot more graphical, whatever. You know, now we're having all sorts of interesting technologies. One of the things that I think I mentioned we work with a lot here on campus is virtual reality stuff. We have a grant from Meta, and we, which used to be Facebook, but they're the kind of the leaders in VR for doing research and development with VR stuff. And one of the cool new things that's coming out, you're actually going to see a lot of announcements here in the next month or so related to VR. Out of curiosity, how many of you have done anything, have had a VR headset on at some point? Once? How many of you like own a VR headset and actually use it? Wait, what do you mean you have to have the room? No, you don't. Yeah, but I don't even do that. I use the Quest 2 to do PC VR. I just sit in my my couch. Yeah, super lazy. Yeah. But in any case, you know, probably the cool kid today for, I would say, the best VR headset from a price point and usability is the Quest 2. It's a fully wireless headset, but I use it to play PC-based VR. But I'm just in a different room in my house. My high-end PC with, you know, fancy graphics cards is in my basement. You know, I'm sitting in my living room with this wireless headset over my network using VR stuff from the computer. But one thing, and this is kind of related to what I was just talking about, one thing you're going to see is becoming going to be in all of our new headsets that are coming out is something called eye tracking, where it has a module in there that's looking at keeping track of where you're currently looking. Okay, what's that going to be good for? Based on some of the conversation we've had here in the last few minutes, why might it be handy to be able to track where you're currently looking? Let's think about it from the computer, the performance or capability perspective. Good.
Because depending on where you're looking, less when you're not looking.
Yeah.
So,
and that's kind of how things work in real life as well, right? So if you're sitting here and you stare forward and you kind of just look out of your peripheral, things aren't as sharp over there, right? Kind of blurry or whatever. I'm not sure how God really wired it up, but using that example, we're not rendering all the stuff in high definition over here. Only the things that are in that we're currently staring at are fully rendered. Well, if rendering takes a lot of processing power, or, you know, whether it's processing on the CPU or processing on the GPU, the graphics card, the idea would be, especially in a mobile device, you can get way higher end graphics with the same hardware if you're rendering less stuff. You can render higher resolution stuff, but just less of it because you only have to render what you're currently staring at. So this is going to be a big jump in the performance of these things. So that's one thing that they're getting ready to become mainstream. It already exists, but it's not mainstream, so all the software is not really taking advantage of it. Another thing, it's most obvious in VR because that's kind of where a lot of the innovation is taking place right now. But really with any sort of gaming, a lot of times you're measuring the performance of a game in terms of frames per second, right? You know, you get you watch these YouTube channels or whatever that talk about the latest greatest game, and they're talking about this graphics card, and I'm currently running this at 290 frames a second. Your human eye can only see about 42 frames a second. You can kind of feel maybe up to 120 frames a second, like almost like a smoothness feel, like, oh, it feels a little smoother to me. Much beyond that, I guess there's going to be some people with just really acute awareness, but you're getting very diminishing returns when you're looking at having render a frame is a picture. So when you look at your computer, if you're watching TV, a lot of times TV is like 24 or 30 frames a second would be your standard TV. So it's showing 30 pictures in 1 second, and your brain puts those together as its motion stuff, right? And when you go out and buy a new big screen TV, they ask you, well, are you a gamer? Do you watch a lot of sports? Because then you want the higher hertz rating, so it has the faster refresh rate, so the football doesn't look like 9 footballs when they throw it. It actually, because then you're seeing the last frame as it's not updating. So these are all things that are truths, but now we're using artificial intelligence to predict the next frame, to actually increase more speed. So we're using all these other angles to make our computers with today's current power even more powerful without changing anything in the hardware. Yeah. Yeah. Especially not with Minecraft. Yeah. 256 gigs of RAM guy. It's like, I'm running Minecraft at 1400 frames a second. Or walks in Microsoft Word, it just shows the infinity sign. When I when I look at my frame rate for Microsoft Word. All right, so punchline with all of that is the problems we solve today are far, far, far more complex than the problems we solved before. All right, procedural languages, they gave us enough tools to tell computers what to do back then. So rather than tell you what procedural languages did, let's look at what object-oriented languages added to that. In real life, we as human beings, we think about things in terms of objects, right? It's in my pocket. Okay, so what's this guy? Phone, smartphone, whatever you want to call it, right? How do you know that? Because you've seen them before, right? You recognize this object, right? Now, this object has a couple of buttons on it, right? What buttons do you think it has? Power, volume-y stuff. So without you ever actually inspecting my phone closely, you can make a pretty good guess at what interface buttons are on here that I would use to operate the device, right? Because as human beings, we think about the world around us in terms of objects. This is a smartphone object. These are the way. So inside this, we believe there's going to be a whole lot of really complicated, 6 nanometer stuff, multi-core stuff, a lot of complicated circuitry that is inside this that on a daily basis, we don't have to interact with, right? But we believe that's true. We believe we crack this thing open, we're going to see some stuff that we don't want to have to deal with. All right. So all of those details that are in here can be accomplished with procedural programming. What object-oriented programming does is it allows us to stuff those details inside of a shell and refer to that shell as an object. So this is a smartphone object. All those wires are still in there. But with an object, all that's exposed to us is the public interfaces that we actually need to use it. Some smart person still had to go and build this device. They still had to design all the circuitry and all that stuff. They had to do the procedural coding of this device. But once they got the problem solved, they took all those details and they shoved it inside of this little case and only punched out the holes for the pieces of it that I actually need to interface with when I'm using it, right? The example I usually use with an older phone example is, when you have if you walk into a room and I have this big pile of wires sitting here and I tell you this is a phone. And at first you don't believe me, you come up, you start fishing through, you find some buttons, you hear the dial tone as if that exists anymore. I actually heard a busy signal the other day for the first time in maybe 20 years. It was I didn't know those still existed. I got one. But in any case, you have this pile of wires. So finally I convince you that yes, this is a phone. It doesn't look like a phone because we think of things in terms of objects. It doesn't look like a phone object to us. But the stuff that's laying there functionally is a phone. That makes sense? Procedural languages would allow us to create the wire-based pile of wires for a phone. Object-oriented languages give us one more step, an organizational tool that allow us to stuff those wires into an object and then just pass that object around. Okay, if you did need to get inside the object and start manipulating stuff, you could with some extra effort, but the general use, once you buy your phone off the shelf, on a, I'm guessing most of you go through your entire lifetime of a phone and never actually open it up and do anything on the inside of it, right? Some of you might be hobbyists and like, oh, I'm going to change my own battery and that kind of stuff. But in general, people will go long periods of time, including forever, with their devices and never open them up to get to those details. We just rely on someone else being smart enough to build it for us. And when it wears out, we go get a new one, right? That's what object-oriented languages do. They give us the ability to have those organizational tools, because that is how human beings solve problems in real life. We think about things in terms of the objects we need to grab. All right. If I want to take a drink of this soda, I'm going to grab this soda bottle object. Okay. I'm going to, use the cap. I'll interface with the cap to unscrew it. I had to know how to do that, whatever, and I can drink from it, whatever, and put the cap back on. That's the capabilities of this object. All right. Now, if we melted this all down and it was just a pile of goo, it's still the same stuff. It's just in a different format that no longer makes sense to us. You would just call that a mess, right? All right. So human beings like to think about things in terms of objects. So we're going to say object-oriented languages provide a mechanism for storing the details of our programs inside of object containers that publicly expose the portions of the object that need to be manipulated to use them, and hide the details that are important but don't commonly need to be used. Let's see if I can I'm gonna go fix the share link right now while I'm thinking about it. Former computer science student, by the way. Works at Acuity. Yeah. Corey Newhouse. His dad is the director of IT here. So when something goes wrong with the Wi-Fi, you can hate on him. He's actually really good at what he does. But that is a thankless job. When everything's working, you're doing your job. When something's broken, you're incompetent. It's the way it works. Course slides. Oh, that's not the one I want. It might actually take me to the right place, but I'm going to update this. Can't I update that? There we go. All right. So I updated the link on Blackboard that'll take you to the slide deck that I'm currently changing, since there was a weird thing. With the ultimate goal that you don't have to type all this crap in when I'm saying it. You have the slides available to you. All right. So when we talk about procedural versus object-oriented languages, we aren't talking about night and day type situations. We're really talking about the difference between older languages and newer languages, where newer languages have given us a couple of features that let the way we program newer computers be a little more convenient for us, because it's the way we already solve problems in real life. In the early days of computers, when we really didn't ask them to do that much, we weren't really putting human beings in that much of an uncomfortable situation, relatively speaking, because we weren't solving these really complex problems with lots and lots of objects that have to manipulate, interface with each other and stuff like that. Modern programs do those kind of things, so we have languages that facilitate that. But what you'll see here, if we go back to this picture right here, this is a procedural language. Object-oriented, 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 object-oriented. So all the new languages built right on top of C. If you took a hello world program in C, you would have to change maybe one line, well, one word to make it work in C++. You'd have to change like one word to make it work in Java, one word to make it work in C#. I mean, when you look at Java code or C# code, if you already knew C from the late 60s, they look the same. This isn't a foreign language. They're very based on each other. Okay. The ones over here that probably look the most different at a glance, but then once you get into it, you realize they're still the same, is Objective-C. They use a little bit different format for calling objects. At some point, I'll show you an example of that, but it's not going to be meaningful to us right now. But bottom line is, if we learn C, and then when we introduce objects, we start operating in C++ mode, let's say, for representing objects, you're going to realize that you are looking at the baseline for all modern programming languages. Okay. I think I mentioned at the end of the class when we were talking about this slide that Swift is our most modern. All these are compiled languages as well. You see far fewer compiled languages come out than you see interpreted languages. Interpreted languages, you get new languages every 15, 20 minutes because writing interpreters is pretty easy, because you just write your interpreter using one of these languages. You write in a C or C++ or a Java interpreter for Python, for example, or you can invent your own programming language. There's a language called Chicken that's out there. It's the Chicken language, and it's actually related to assembly language. So if I come here and I just type in Chicken programming language, yeah, so here's this is hello world in Chicken. Now at a glance you look at this and like, okay, well, that's a joke, right? That is a language that, when interpreted, will put hello world on the screen.
Based on how many chickens?
How many times chicken appears. Okay. So this goes back to what we were talking about with processors. When we looked at assembly language, the hello world in Linux assembly, a processor, a CPU knows a bunch of magic tricks. Okay. We talked about processors in this context, right? And if you call those little tiny magic tricks in the right order, something can happen, but any individual magic trick doesn't really do much. So the chicken programming language says, here's the 20 things you can do in chicken. Magic trick number 1 is 3 chickens. Magic trick number 2 is 4 chickens. Magic trick number 3 is 5 chickens, yada, yada, yada. Okay, so what I did, my wife and I go on a lot of cruises, and I make it a habit where I just sit at the wine bar and I write software when I'm on the cruise as like a hobby. But I always like to try out like some new thing that I hadn't messed with. So what I did is, because this would obviously be mind numbing to sit there and write chickens, right? You just have to copy and paste, like, was that 5 or 7? Is that 18 chickens or 19 chickens? I forgot. Well, so I wrote an interpreter that I could type what I wanted in there, which magic trick, and it converted that to the right number of chickens. So I would write, I had my own interpreter that translated, I invented my own little mini language that I could type what I wanted to type, and it would turn it into the appropriate number of chickens to output the program. So my output was something that looked like this that I could then run through a chicken interpreter to run. So we wrote this was, I don't know, 6 years ago, something like that, 7 years ago. I think I wrote a dice roller in chicken. So just kind of a funny thing. It was like 20 megabytes of chickens. And that's as a text file, that's a lot of chicken. But the punchline here and what we were just talking about, there's new interpreted languages every 15 minutes because some people sit around and just come up with this, yeah, it's a real thing. All right. So interpreted languages are a dime a dozen. But they're still all based off of C. I mean, our first programming language that is meaningful to modern computer science, I'd argue, is C, because it is the strong influence for all modern languages, which is why we start with that. All right, but all of these are compiled languages, and those are much more difficult to create because you have to write that compiler. And the compiler needs to translate from this high-level language into the low-level language of your actual processor. And also be efficient, because one of the jobs of a compiler is to make a bad programmer look like a better programmer. Because you can write fairly inefficient code, and when you compile it, it turns it into a more efficient version than what you wrote, even though it technically accomplishes the same thing. So compilers are difficult. So as we go through here, why did we need something better than C? Same reason we've just been talking about. We kind of needed this idea of representing objects in order to solve more complex problems. So C++ is the object-oriented version of C. Microsoft jumped on the C++ bandwagon. Obviously, Apple hates Microsoft, or depending on the year, they might hate Microsoft. So they weren't going to jump into the same language as Microsoft, so they bolted on to this Objective-C project, which is the object-oriented version of C. Look a little different, but they solve the same thing. From C++, we had a language called Java, which, not that C++ went away, but Java is platform independent. You write the program once, it'll run on any of the computers. Not very good for video games or for things like word processors and stuff like this. Things that are written in Java, a lot of times when you go to a site and you download a piece of software you want to install, if it's available for like every single platform, it's available for Mac, Linux, Windows, yada, 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 chances are it was written in Java for that reason. It's not a video game, so it doesn't have to have that extreme performance. And to make it platform independent, if you write it once in Java, it'll run on any platform that supports what's called the Java virtual machine. Okay, and there's a Java virtual machine for Mac. There's a Java virtual machine for Windows, for Linux, for all your smartphones, iOS, Android, yada, yada, yada. All right. Well, Microsoft tried to steal Java, as big companies do, and they came out with C#. I think I mentioned that in class as well. C# looks exactly like, looks a lot like Java, but Java looks a lot like C++, which looks a lot like C. So I would say, who cares? But in any case, it got him out of the lawsuit. C#'s out. Now, Microsoft would say, and this is where it kind of becomes funny, one of the big selling points of Java was that Java's platform independent. You write the code once, and it'll run on any platform that supports the Java virtual machine. C# is also platform independent. You write the code once, it'll run on any computer that supports the .NET component architecture, which means it'll run in any computer at all, as long as it's running Windows. So platform independent in theory, but not in practice, because Microsoft only has the .NET component architecture for Windows until more recently. They actually have ported it over to Mac. I guess enough people are buying Mac laptops now that they want to be able to pick up some of that revenue. It's okay, it's just business. But it's kind of a funny thing where they had all these campaigns about how C#'s platform independent, where you can run it on any platform as long as it's Windows. you're good. You know, then you have this weird guy here, which really I think gives the kind of captures the I don't know, how would you say it? Like that captures the spirit of Apple, I think. You know, like when you go into how many of you have been in an Apple store before? And you kind of look around and you wonder where they're serving the Kool-Aid. You kind of know what I mean? Yeah, it's got I mean, I'm a Mac user, but because I run Windows and Linux all on one machine, I only have to carry around one thing. I like the operating system, but something feels a little off inside of an Apple store, right? Well, that's really evidenced here with Swift. The people who are writing iPhone and Mac applications here in Objective-C, they weren't complaining. In fact, because it looks a little different, there were a lot of people who don't really know Objective-C, so it's kind of an extra superpower, let's say. Swift looks a lot like Java. And Java is the native language for writing Android applications, which would be Apple's competitor, right? So Swift says, hey, Android developers, why don't you come over here to the dark side? You can make more money, and we'll give you a language that makes the transition a little friendlier, where the Objective-C transition wasn't as friendly, because Objective-C is a fairly old language. All right, so that's really the mentality behind Swift. The Apple developers were not complaining about Objective-C. This wasn't doing them any favors. In fact, if anything, these people were put out because they were now forced to learn this new platform because all new iPhone applications were going to be written in Swift. You could still manage the old ones in Objective-C, but the default language was going to be Swift. But where Apple really lost me with Swift is when they started allowing you to name variables with emojis. That's just stupid. I mean, we're like back to hieroglyphics now. You know, like you can have a variable with the poop emoji. That's the name of the variable. So I don't know. So that's Apple's whatever. So I would say I'm not a big fan of Swift, the language. I know it. I've written a bunch of crap in it, but I don't think it brings a whole lot of stuff necessary to the table. It's just Apple saying, hey, we have the most recent crap, whatever. Okay. So questions about any of that stuff, how we got from C to where we are today. Let's call it ish. All right. So jump down here to get past our there's the three kind of programming languages here. I think we already kind of talked about that with the compiler. You know, we need multiple things we need to know what language are we compiling? What architecture are we targeting? So am I turning C++ into low-level code for Intel? And then on top of that, we also need to know the operating system. So when I compile C++ code for Windows running Intel processors, I'm going to get a different output than if I took the same C++ code and I compiled it for the Mac OS running their M1 processor, something like that. Ultimately, they're both going to be the hello world program or whatever, but what you will see as that output is stuff that the M1 processor can understand in the context of Mac OS instead of what the Intel processor can understand in the context of Windows as the operating system. Okay, so compilers have to solve that problem, which is why we don't have a zillion compiled languages, because those are hard programs to write. Okay, we talked about that. More conversion stuff. Kind of just doubling up on it because I add stuff in. All right, we're going to insert right here. I'm going to say all programs begin and end with main. So this is really a throwback to the C programming language. The concept has existed since the beginning of computer programming, but when you start a program, so when we compiled a program last week or whatever, and then I ran it. When you run that program, the operating system is going to immediately go and find your main method, because that's where your program starts. It starts at the main method. Okay, so main is the method, I'm going to say function, subroutine, procedure, etc. Those are various names for basically the same thing, a chunk of code with a name attached to it. So we have a chunk of code called main. And so this is a method that dictates how the program flows. So whenever a program is run, it starts at line 1 of main, and then deviates to other areas of the program as instructed. All right, make some sense? And you can take this to the bank, that every single programming language at some level, every modern programming language, the program will begin at main. When we write stuff in C and C++ and Java directly, we will physically write main ourselves. For example, if you're doing an Android application and you use Android Studio to create a new app, it will put you into something called an activity that has this function called onCreate. And that's where you as the programmer start your writing. But what ends up happening behind the scenes is when that activity first launches, it calls main. Behind the scenes main, which knows how to launch an Android application. Same thing's true over on the iPhone side of things. Okay, so this idea of all programs begin and end with main is still a truth. All right, so that being said, actually, let's go ahead and just write it in code. It's called the C. Well, we'll do it. We'll do C++. C++ programming template, since we're ultimately going to be doing object-oriented stuff. Okay. One thing that's going to be handy for you as a programmer as you learn different languages is kind of really memorizing the hello world program in each of these different languages, so that you can sit down in any of these programming languages and immediately give yourself a working program that gives you your starting point. If you don't have it memorized, you can go online and find or something, but for languages you use often, so let's say C, C++, Java, C#, all these, you should be able to write a default hello world program in order to work in that language on a daily basis. So for us, at some point, there will probably be a quiz on what we're about to look at. And a lot of times I put it on exams too, is I'll have a question that's something like write an error-free hello world program in C++. It's kind of you just doing the brain dump of, this is my starting point for all C++ programs, that kind of thing. All right, so let's go and look at this. I think I had mentioned before that in here, we're going to be, and I don't care if you use a different tool, but I'm going to use this onlinegdb.com website. I promise you it is not the best programming tool, but it's the tool that I don't have to support because it's in a web page. It's not bad, but if you're working professionally as a developer, there are other tools out there that make your life easier than this does, but this all runs inside of a web page and whatever. Okay, so what I'm going to do here is I'm going to select my language up top here. I'm going to select C++. Notice there's a bunch of different versions of C++ here. The C++ has gone through various, so this was in 2014, 2017, 2020. It went through these different renditions of trying to keep up with the Joneses, adding some new features to make it compatible with some of the more modern languages. Okay, but I'm just going to choose the normal C++ thing up here. All right. And so what it does actually in here, it automatically gives me a default hello world program. So this is the thing, and you can ignore this crap up here. Those are so stuff that starts with a slash and then an asterisk and ends in an asterisk slash. This is a multi-line comment. So all this stuff is just visual. You can do single line comments. By just doing a slash. And you'll see plenty of examples of that, but that's just, this stuff here is filler. All right. So this is really our program here. Okay. Now I mentioned all programs begin and end with main. So here's main right here. All right. I'm actually going to put a couple of things in here. I'm going to say int argc all right. So technically you didn't need this stuff in here, but I want to really use this as a baseline for stuff. This used to be what you would always need to put. So for starters, if I want to be able to write stuff out to the screen and also read stuff in from the user, I'm going to need a library here called Iostream. All right. Don't worry about what else is in there right now as we introduce little features. So you can think of it like we just ran to Home Depot. Okay. And we brought home this toolbox called Iostream. And right now we're only using one thing from in it, but eventually we might pull some other stuff out of there. So I need to say here at the top that I'm going to include Iostream in this program because I might be using some stuff from that toolbox. All right. This next thing, using namespace standard. I don't actually have to put that because I could do something like this. Standard cout if I wanted to. But Iostream lives in this namespace called standard. So really those first two lines go hand in hand. I want to include this library from this namespace. So pretty much every C++ program you ever write will start with these two lines. Okay. For a long time. Eventually, if you start writing graphical user interface stuff, you might not use the old Iostream stuff, but for right now, this is true. Then I mentioned all programs begin and end with main. Now notice here, well, then inside here, so I'll just jump down. So we have an opening curly brace and a closing curly brace. I mentioned that main is a method. So what we look at right here, this chunk of code here is something called a method. Sometimes you'll hear it be called a function or a procedure or a subroutine. These all mean the same stuff. They are a named chunk of code. So this chunk of code right here is named main. It takes this stuff as parameters. We'll talk about that in a second. And it returns this when it's done. If we were doing this in Java, main would look like that. So this is hello world in Java. This is hello world in C++. Okay, a couple little things changed in there, but ultimately the same information is occurring here. Java is a much newer language, which is why main returns nothing. That's what this thing here, when you have a function, the thing that comes right before the function name is what kind of value does that function return? The stuff that's in between the parentheses after the function name is what kind of stuff does that function take in order to work? And you're going to see lots of examples of this, so don't worry about it right now. I'm just putting this in context. So you see me do this with the terminal. The terminal app again. All right, so if I do something like VI, and then I do like test.java or something like that. Here is a program that I'm running. The program's called VI. So somebody wrote this computer program. That's a text editor is what VI is. And that program is taking in a single input, test.java, which is telling this program that I want to edit this file called test.java. So it was common in older programs for us to have to give it this information. Modernly, what do? We open up Notepad, then we go to File, Open, you go find the file you want to open, right? So our modern day of doing things is when we launch a program, we don't tell it what application we're launching it on, unless we double click on the file and let it launch the program automatically for us, right? So our modern cadence of working with programs in a graphical user interface type thing doesn't rely on this stuff. But remember, we're using a language from a few minutes ago. So the name of my program here is VI, and it's taking a command line argument, test.java. So if I put that in the context here, in main, if you look in Java, this is taking an array of strings. This will be a collection of those command line arguments. In C++, this is my collection of command line arguments. And this guy here, why do I have two instruction or two parameters here instead of one? Is C++ collections aren't smart enough to know how many things are in them. So in C++, it also had to be provided with the count, the argument count. So in my example right here, VI test.java, argument count will get passed, actually get passed a 2, because VI is one of the arguments. It counts as one of the arguments. And this guy will hold two things. It'll hold VI in bucket 0, and it'll hold test.java in bucket 1. Okay, that's what this stuff up here is used for. Modernly, we rarely use command line arguments when we write code, but that's why this exists right here. All right, make some sense? All right, I will see everybody on Thursday. Remember, we're starting in here. We're going to be doing some 3D printer stuff. So Blade, our makerspace manager, Professor Liao, will be starting that stuff, and then we'll pick up from here after that. So, sure.
Is there any way